meeting is now being recorded.
Okay, hi everybody. It is time to start. Good afternoon, ladies and gentlemen. Welcome to the Office of Information Management and Analysis, OIMA Brown Bag Series. The webinar will be strictly a 30-minute event for both presentation and questions and answers. Normally, we don't do announcements on this webinar because with the time we have is too short. But before I introduce the speaker, we have one announcement to make. June's webinar is cancelled. The reason is our program hosts 2 days annual science symposium on that day, so because of that it is cancelled, so we will see you in July. So today's presenter is Dr. Karen McLaughlin. So Karen is a senior scientist at the Southern California Coastal Water Research Project, SWRCB. She received her BS in Geosciences from Penn State University and her PhD in Geological and Environmental Sciences from Stanford University. Her current research utilizes novel tracer techniques to understand the source and fate of anthropogenic nutrients and coastal water. She is particularly interested in understanding the effect of productivity on nutrients, cycling, hypoxia, acidification, and harmful algal bloom formation, and use of stable isotope tracers for evaluating the relative influence of different nutrient sources on ecosystem health and function. So with this brief introduction, I will pass the phone line to Karen to start her presentation. So Karen, you can go ahead and start.
Great, thanks, Dewey. Okay, so today I'm going to talk to you about ocean acidification and some different monitoring strategies and technologies for coastal and estuarine waters. I'd like to start with some quick background on ocean acidification. Ocean acidification is often called the other CO2 problem. The CO2 story that most people are familiar with is the rise in atmospheric CO2 concentration from the burning of fossil fuels. However, not all of the CO2 that goes into the atmosphere stays there. About 25% of it dissolves in the ocean, causing a decrease in ocean pH. So how does CO2 affect ocean chemistry? When CO2 dissolves in the ocean, it reacts with water to form bicarbonate ion and a hydrogen ion. The hydrogen ion is reflected in the change in pH, because pH is a measure of hydrogen ion concentration in the water. However, not all of the hydrogen ion stays dissolved in the water column. Most of it reacts with carbonate ion to form more bicarbonate ion. And this last reaction is a problem for organisms that rely on carbonate ions for their livelihood. This is particularly a problem for marine shell-forming organisms that use calcium carbonate for shells. As ocean acidification progresses, there is less carbonate available in the water column, and they have to work harder to maintain their shells. As a result, the energy that they would normally spend growing their shells and reproducing is now used just to maintain their shells. So how is this effect measured? Scientists use a parameter called the aragonite saturation state. Aragonite is a polymorph of calcium carbonate. It's typically used by larval species in the early stages of development. So it's a sensitive indicator for the effect of lower carbonate concentration in waters. When aragonite saturation state is greater than 1, then aragonite can spontaneously precipitate from seawater. When it's less than 1, it spontaneously dissolves. And this is a condition that a lot of people refer to as being corrosive. When you hear the term corrosive seawater, it doesn't mean battery acid corrosive, it just means that aragonite saturation can spontaneously dissolve. However, the truth is that most organisms require aragonite saturation states to be much greater than 1 to be healthy. So over here I have 2 pictures. The top one is a healthy pteropod living in a saturation state around 2. You can see its shell is nice. It looks kind of glassy. The bottom picture is an image of a pteropod that's dissolving in water. So you can basically see here now, this is a aragonite saturation state around 1.2. You can see that there's a lot of pits along the shell at the ridges, and you can see some serious cracks and ridges in the shell. Okay, so acidification is not a future problem that we're going to have to deal with down the road. It's a problem that's happening right now all along the coastline. So right now I'm showing you two maps. The left one is from a survey in 2007, and the right is from a similar survey in 2011. And the maps show the depth to where the aragonite saturation state is 1. So this is typically called the aragonite saturation state horizon. So when this is where waters begin to become corrosive. The red is where the waters hit that threshold at about 40 meters, and the white is where the threshold is at the surface. So you can see a number of places along the coast where that saturation threshold is very close to the surface, and some places where it's actually even surfacing. And this is a problem because the pteropods that I show you on the previous slide, those are pelagic species. They live in water column depths up to 100 meters. And they are a pretty critical organism forming the base of many marine food webs. And you can see that 100-meter threshold is the green, and you can see that that's all up and down the coast. So this is clearly a problem affecting the coast all along our coastline. But more importantly than just observing changes in ocean chemistry, we're also seeing clear impacts on biology. So particularly in the Pacific Northwest, where I showed you those waters on the previous slide are hitting the surface, we're actually seeing some major impacts on the shellfish industry up there. They have suffered incredible losses related to impacts on larval oysters that are directly traced to aragonite saturation state and acidification conditions. The images I'm showing you here are from a paper by Alan Barton et al., where they were investigating the impacts to their oyster spawn in a hatchery. The two samples, they're basically oyster larvae from the same spawn group. The left-hand panel here is from larvae that's grown in surface waters where aragonite saturation state is 1.7. And the right-hand side is that same group, spawn from that same group, grown in waters taken from a deep intake where aragonite saturation state was 0.5. And you can clearly see the impacts on the organisms when aragonite saturation state is below that critical threshold. Okay, so now that hopefully I've conveyed the urgency of the problem here, the next step is to understand the drivers for this change. Ocean acidification has largely been a deep ocean problem, and this is primarily because carbon dioxide dissolves more readily in colder waters, so they typically dissolve in higher latitudes. They don't stay in high latitudes because of the global ocean conveyor belt, where water moves along deep flow paths and brings to lower latitudes and coastal upwelling zones. This process takes many years. So the impacts that we're currently seeing along our coastline are from atmospheric conditions 50 years ago. So 50 years ago, atmospheric CO2 was much lower than it is today, so that sort of leads us to predict that we can expect the situation to get a little bit worse as we move forward. Okay, now I mentioned that the deep ocean flow path comes from high latitudes to our coast, and we are particularly vulnerable here on the west coast because of two factors. One is we have a fairly narrow continental shelf, and wind-driven upwelling tends to move that water to the surface and being replaced by these low CO2 waters from the deep. So the west coast of the U.S. is particularly vulnerable. Okay, so how does this work? Acidification along the coast. I mentioned that we have upwelling here, so that's bringing that high CO2 water, low pH water from the deep into our coastal shelf. But there are nearshore processes that can actually exacerbate this effect. So here I have a conceptual model of ocean acidification in coastal waters. I'm showing you in this yellow arrow here, upwelling is bringing high CO2, low pH waters. So that's a direct way that acidification can impact coastal waters. But particularly in Southern California and the Pacific Northwest, where we have a lot of urbanization, we also have additional nutrient impacts. So here in Southern California, where I'm working, we have a number of significant ocean outfall pipes from wastewater treatment. We also have a lot of surface runoff, particularly during our wet season, that's impacted from agriculture. And then we have local emissions, both acid and nutrient. into the coastal waters. All these nutrients work to develop phytoplankton blooms, and when these blooms finesse and settle below the euphonic zone, they are respired, and respiration consumes oxygen, leading to deoxygenation and hypoxia, but it also increases CO2 in the deep waters, and this can lead to additional acidification. So we have two different pathways through which acidification can affect our coastal waters. Okay, so the realization that these local activities can impact the progress of ocean acidification has led to several regional actions to try and manage nutrients and acid inputs into coastal waters. The idea behind this is to slow the progress of acidification to try to keep ecosystems from hitting tipping points, and thereby allowing ecosystems a little more time, hopefully, to adapt to the changing ocean chemistry. This has led to an increased drive for ocean acidification monitoring. To date, ocean chemical and biological data on the impacts of ocean acidification and the variability in exposure to these conditions are really quite sparse. But we know from the data that we do have that the conditions are widely variable and both spatially and temporally. So understanding the magnitude, frequency, and duration of exposure is really critical for trying to develop successful management strategies and to manage risk. Okay, but we don't have to do this in a box. So a lot of people have been working on developing strategies and guidance for developing monitoring programs that can be networked together. So in this fashion, these local managers, they can understand the variability in exposure to acidification in their own backyard, but also have data that's directly comparable to other monitoring programs up and down the coast, so that scientists and managers can understand how the changes in ocean chemistry are playing out at a large scale. So that's why coordinating monitoring efforts is really, really key. So one of the groups that's trying to help set up different programs for monitoring is the California Current Acidification Network, or CCAN, and they have a guidance document out, and it's available online with five core principles outlining how a large-scale network can be developed by integrating numerous local efforts. So I'm not going to read you all the different principles here, but the main points are that you need to collect data that's similar enough and similar enough in quality that the data can be shared and applied more broadly to map out more broad regional scale effects of ocean acidification. In addition, there's some guidance that's been developed for estuary systems as well. So the CCAN program can be applied to both estuaries and coasts, but the focus is mostly on nearshore coastal ocean. A recent workshop at the San Francisco Estuary Institute provides a model for how to set up an estuary monitoring program. The approach is to divide your efforts into near-term and long-term goals. So in the near term, you synthesize your existing data and inventory all your assets to implement a carbon chemistry monitoring program, while over the long term, you start looking for additional opportunities to fill in any data gaps from your synthesis, and then add in biological monitoring as well to develop a complete acidification monitoring system. So I'm outlining two local efforts to try to coordinate ocean acidification monitoring. There are definitely other templates out there, so you don't need to be limited to these two. But if you have any questions or interest in seeing these documents, please feel free to email me, and I can send them along. Okay, so once you have a plan in place for developing a monitoring program, what should you be monitoring? So the first step is often to develop a carbon chemistry monitoring program. Experts agree that you should measure more than one carbonate parameter because basically you can measure any two of four carbonate parameters and calculate a aragonite saturation state and thereby characterize the entire carbonate chemistry for your local waters. But most people recommend measuring more than one parameter. That said, I don't have a lot of time, so I'm going to focus primarily on pH today, mostly because pH is already included in water quality criteria, so a lot of people are already required to measure it. And furthermore, pH is also a little more advanced in terms of autonomous sample collection, followed by PCO2, so it's a little bit more ready for an out-of-the-box type application. Okay, so what should you consider when you're choosing what type of sampler? And there are many things to consider, and this is just 4 of them here. But the first and foremost is cost. So these instruments vary widely in how much they cost, but it's not just the cost of the instruments that you need to keep in mind. You also need to keep in mind that there is a calibration of these instruments and maintenance of these instruments that also plays into the long-term lifespan cost of the monitoring program. So doing a cost-benefit analysis is often one of the first steps. The second thing to consider is level of expertise. Some of these new technologies are sort of prototype phase and require a lot of expertise to be able to manage them. The technologies I'm going to talk about today are pretty out of the box. They're all commercially available, so the level of expertise required for them is fairly minimal, but there are others out there that you could choose, and keeping in mind how much you're willing to invest in developing technologies is something to consider. The third is the type of deployment. If you are on a ship and you need to profile at 1 hertz, your technology that you have available to you is extremely limited. Whereas if you are in a deployment type or stationary deployment, then you have a lot more options. And the last one here, and this goes back to cost, is the expected variability in your system. So if you are in an estuary with a high range of pH, then you have a lot more options because you don't need to worry so much about measuring super fine scale, super accurate measurements for your system because you have wide variability. Whereas in a system that's more open ocean, you're going to need something a little bit more precise. Okay, so monitoring technologies for pH, these are, again, all out-of-the-box commercially available type technologies. The first is potentiometric glass pH electrodes. This is what most people are familiar with. They come on any sort of YSI data probe. Seabird has a set for their CTDs. They're super low cost. They're about $300 a pop. They're relatively easy to use. They're easy to calibrate. They're easy to handle. But the problem is they have super poor performance. But that said, they're the only technology available for measuring water column profiles at a rapid speed. So you're kind of in this boat if you are doing ship-based profiling. The second type of technology are ion-sensitive field effect transistors, or ISFET sensors. They're moderately cost at about $5,000 a piece. They're pretty easy to use. With a little bit of training, you can get super high-quality data, and they perform really well. The problem is they are not pressure compensated, so you can't collect a water column profile. But in parentheses, I have yet, because this is an active area of research, and they're currently working to develop an ISFET that can collect a water column profile. The third is spectrophotometric methods, and these can be done 2 different ways, either by collecting discrete bottle samples. This can be costly because each bottle, if you're going to send it to a lab, is about $60 per sample. If you have your own spectrophotometer, it's obviously much cheaper, depending on the cost of your own labor. But if you are going to run it yourself, it requires some expertise, but it is a very good measure, and just to further support this, we're using that as our standard to compare all other technologies against. And you can collect a water column profile if you have a rosette-type sampler with a number of water bottles that you can trigger at different depths. Spectrophotometric measurements can also be collected autonomously. There are several autonomous type instruments that cost about the same as an ISFET sensor. It's basically a little spectrophotometer that's kept encased in a housing, and it has a little reagent bag, so the measurement is conducted by the spectrophotometer. It does the chemical analysis in situ. It's pretty easy to use, and it does give pretty good performance, about the same as the ISFET. But because it is a chemical reaction, it takes time, so it's too slow for most profiling applications. Okay, so starting with potentiometric sensors, I'm just going to give you a quick overview of the types of error you can expect. Again, this is a standard for most water quality ship-based monitoring. Here I have a figure here that's showing how the sensors performed relative to a standard pH, which is that discrete spectrophotometric measurement from a bottle. And the answer to how well it performs is not well. You can see the difference in the pHs between the standard and the CTD pH sensor. pretty bad. The range is over 1 pH unit. The average absolute difference is about 0.1 pH units. And for context, since the Industrial Revolution, the deep oceans have changed by 0.1 pH units. So that is the entire ocean change. Remember, pH is a logarithmic scale, so that's a 30% increase in acidity. And secondly, for context, the California Ocean Plan says that pH shall not be changed at any time by more than 0.2 pH units. And you can see here that you're going to have that just in error. Moreover, you have a bias, that's the dotted line, of about 0.06 pH units that cannot be attributable to random error. So you're under predicting pH using these sensors. So not necessarily great. But there is hope. I don't want to leave you thinking that potentiometric sensors are wholly bad, because a lot of people probably still use them. You can improve the data quality by using an in situ calibration. And this is just collecting a paired measurement. So you collect the potentiometric sensor measurement, and then you collect a bottle measurement coincidentally with the same thing. And then you create a linear regression that compares those bottle measurements to the potentiometric measurement and correct the data set for the difference. So the top figure here is before that correction is applied. You can see the 0 would be where they were completely in agreement, but there's this bias. And then after the calibration, you can see that the bias is gone and the spread is a little bit less. So most of 95% of our samples here are falling within plus or minus pH, or 1.1 pH units. So that's getting us a little bit closer to what we would need for regulatory monitoring. And for estuaries, it's even a little better, because estuaries often have diurnal swings on the order of plus or minus 0.5 pH units. You might actually be able to collect some fairly reasonable data using a potentiometric sensor in an environment that has pretty high diurnal variability in pH. Okay, so the next sensor is the ISFET sensor, which are currently the standard for continuous stationary monitoring deployments. This is the same type of figure as on the potentiometric sensor, so you can see the difference between the standard and the FET measurement here. I have two colors here. One is the gray is people who were just getting those FET sensors for the first time and deploying them without any experience. And the red is groups that have had experience deploying ISFET sensors in the past. And right off the bat, you can see that it's much, much better than the potentiometric sensor, particularly for experienced users. 100% of the samples are within plus or minus 0.1 pH units. The average absolute difference for all sites was about 0.005 pH units, so much, much better for monitoring in an environment where you need to have that high-quality data. Furthermore, the results are pretty uniform for a networking context. So remember, I was talking about how it's very important for different monitoring programs to be able to compare their data. This shows you that for any type of deployment, there is very little difference, no statistically significant difference between experienced users on those 3 different platforms in 6 different environments. The only difference was between experienced and novice users. So experienced users, again, are having really high accuracy, but novice users have a little bit of difficulty. And for what it's worth, the lack of experience mostly affected the data at the very start of deployment. So that was a problem with insufficient conditioning of the sensor, and at the end of deployment, and that was a problem with biofouling. So once you're familiar with your sensor, you know how long you need to condition it, and you know when you're going to need to take it out of your system so that you maintain a pretty high quality of data throughout. Okay, so lastly here I'm talking about autonomous spectrophotometric sensors. These are very similar in performance to the ISFET sensors. The range is really within plus or minus 0.1 pH units with an average absolute difference of 0.004. And again, 95% of the samples are, or 100% of the samples, excuse me, are within this 0.1 pH unit. So again, very high quality data can be got off of these autonomous sensors. And again, there's ISFET and autonomous spectrophotometric sensors that are all available commercially with supported software, so you can pretty much deploy them out of the box. Okay, so how do you choose? The figure I'm showing you now is 6 sites up and down the California coast, and you can see from the black bars, that's just a histogram of all pH values recorded at that site. and the black bars are 95% of the samples collected. The red bar is the uncertainty you can expect from either an ISFET or a spectrophotometric sensor. The blue box is the error that you can expect from a potentiometric sensor if it's calibrated. So you can see that for a site that's in an enclosed bay or at the mouth of a slough where you have pretty high variability, you could probably get some decent data to characterize your system with a potentiometric sensor. But for an open ocean site that's on a pier, that potentiometric sensor is basically going to give you garbage. So that's an important consideration when you're trying to figure out what type of sensor to choose for your system. Okay, so once you have this wonderful data set, how do you interpret your risk? So for this, you're going to need an assessment framework. And unfortunately, there isn't one. But that said, we are actively working on this problem. SWRCB is partnering with the OPC to get scientific consensus on relevant endpoints for saturation state and other carbonate parameters. The idea is to try to understand impacts on magnitude, frequency, and duration of exposure that might affect sentinel species like pteropods and oysters. And once these endpoints are developed, they can be used to understand your monitoring data and characterize the risk. Okay, so to sum up, ocean acidification is a global problem that's expected to impact the U.S. West Coast and beyond, and it's expected to get worse over time. Chemical and biological monitoring data sets are incredibly sparse and really should be enhanced to understand the risk and plan for management action. There's guidance for setting up monitoring programs available for both coastal ocean and estuary monitoring systems, and many off-the-shelf technologies that can accurately measure carbonate chemistry. And with that, I'd be happy to answer any questions.
Okay, great. Thank you, Karen. So we will unmute you, and people on the phone can ask. And if you have any question from the room, you can go ahead.
All guests have been unmuted.
Okay. So if anybody has questions, you can speak up.
What is an aragonite saturation state?
Aragonite saturation state, it's basically a measure of how soluble carbonate is in water. So aragonite is a polymorph of calcium carbonate. There's two main types of calcium carbonate. There's calcite and aragonite. Like oyster larvae use aragonite when they're in their juvenile stages, and they switch to calcite. It's just a different form of calcium carbonate. It's a different way that the lattice forms. So the saturation state basically tells you whether or not it's going to dissolve or precipitate.
We would sleep without, on the floor. And not, for home, it wouldn't be in a crate. It could be. Can you put two options? Is it multiple choice? Okay.
Oh.
So I would say
I think that's not a
with
question,
us
yeah?
and or crate.
That is conversation with us.
Choice. You know what I mean? Yeah. Our dog wakes up on the floor in the bedroom.
Kiss. I cannot unmute it.
It varies. You can say,
so anybody has questions from the phone?
Like 2 hours.
Probably you can't
up to 8 hours.
over talk over her. I don't know.
Really?
For maximum?
Sure. Our situation, yeah.
Can you see?
You write in, say currently, the situation isn't very, because you're home now. It varies from day to day. And then just say 2 to 6. Yeah. I have to answer that one, It's the current situation. Because once the dog is bigger, he'll be better with that.
I can't actually hear anything over the one speaker.
Sorry, Karen, somebody is talking on the phone and it was not related to the talk. So if anybody has any more question for Karen, please go ahead and ask from the phone or anybody, any question from the phone?
Hello, Karen. What are the 4 carbonate measurements you could do 2 of? You said you could do 2 out of 4. What are the 4 carbonate measurements?
So pH and PCO2, those two have autonomous sensors, but you can also collect total alkalinity, which is a fairly easy bottle measurement,
We have another
and dissolved inorganic carbon, which is also a bottle measurement right now.
I did.
All right, thank you.
Okay. So time is up. Thank you, Karen, for doing this. Thank you, all participants. So we'll see you in July. Thank
Sure.
you.
And if anybody has any further questions, you can feel free to email me. I might be happy to answer.
Thank you very much, Karen.
Thank you.
The host has left the meeting. So at this time, the meeting will come to an end. Thank you and goodbye.